All right, well, let's get started here. Hope everybody's doing well today. We'll take a look at the announcements before we move on. All right, so remember that the next homework assignment that you've got on your plate, because you've just turned in homework number 4, which was the nodal method assignment. That one was kind of a brain teaser, I think. Homework number 5 is the Hardy-Cross method and a couple of questions having to do with water hammer and surge tank sizing, which we're covering today. That's due on Monday next week, and so you need to upload that before class on Monday. And then the pumps assignment, which covers material that will begin to be introduced in Friday's lecture. That pumps assignment is due the following week, Monday, March 8th. And then our first exam is on Monday, March 8th as well. And the way that's going to work is that the exam will open at 12:30 p.m., so it's 30 minutes before our class meeting time. And it'll be available to you until 2:30 p.m., which is 30 minutes after the class time. And the exam is going to be written as a 50-minute exam. So it's a 50-minute exam, but you're going to have 120. And I guess the one other announcement I should remind you of is that class on Friday is online. So class on Friday is online. And I'll email you the link and post it on Blackboard after class today. That's pre-recorded for the class meeting that we're going to have in 2 days. Okay, so are there any questions about these announcements before we start talking about water hammer and surge tanks? All right, well, let's get into it then. Now, I came across a post where someone was describing the most expensive mistake they've ever made. And so ask yourself that question. What's the most expensive mistake you've ever made? I think in my case it would be the opportunity cost of not getting into Bitcoin, you know? Because I kind of knew it was going to be a big deal, but I didn't buy any. I mined a little, but I didn't buy any. I should. So that's the most expensive mistake I've ever made. Courtney says college. Hopefully it turns out not to be a mistake. Isaiah sold a car because it's out of gas. I bet that's a pretty sweet story. That's funny. All right, well, let me show you what Dub Funking Step said. I'll give you a moment to read that. All right. $800,000. Man, can you imagine just having a kind of a dead-end job as a lifeguard someplace, a summer job, and you end up causing $800,000 of damage? That's brutal. So this person, I don't think, is not a hydraulic engineer, and they haven't exactly described what causes a water hammer, but they have described the stakes. You know, if you have a water hammer and haven't prepared for it, or if the system isn't designed to prevent it, then it can be a very costly problem. So that's what we're going to be talking about today, is what causes water hammer and how can we prevent it. All right, well, let's watch a couple of videos that illustrate what water hammer is. These are some real live illustrations of water hammer, and then an old-timey video. It must be from the early 80s, but man, I really like it. It just shows water hammer so effectively. So let me pull up these videos to show you what water hammer looks like and how you might encounter it in the real world. I've clicked on the link here. Hopefully it's bringing up somewhere. I'll just copy and paste that into a separate tab. That may ultimately be a little bit easier. All right. We may get some commercials we have to suffer through. We don't. Not on this one anyway. Alright, water hammer. So, the sink was opened and then is being closed very rapidly. So let me start at the beginning in there. So the faucet is running and then is being closed very rapidly. Okay. Okay, so those quick changes to the flow rate is what caused the phenomenon that we're seeing of this rapid change of, it kind of looks like a sputtering or something. So that's our first physical manifestation of water hammer. Let's look at another. Let me just copy over the link for this next one. Somebody's washing machine. We're going to have the commercial for this one. We don't have to listen to it though. Oh, all right. Hopefully you get the system audio. I'm not sure.
Okay, you heard that noise come from the pipe. I'm going to get closer. We're going to see the action over here. You see the whole pipe shake. That's from the cold water valve. And there's one solution to take care of this problem. You actually have two. You either lower down your house water pressure, or you have to get yourself one of this guy called a mini water rester that you can pick it up in a plumbing store. And this.
Okay, so what's happening here is that the washing machine is drawing some water from the line, and it's opening and closing the valve really quickly, and so it's kind of sending a shock wave through the entire water system as the valve is being opened and closed almost simultaneously, bringing in a little bit more water for the load. And what this person is suggesting is that there are these shock absorbing systems that can be put in line, and it's almost like a spring in there that the shock would work against rather than reflecting its way down the line entirely. So let me just show you one more video, and I've saved the best for last. This is one where, even though the equipment looks a bit old and dated, it does a great job of explaining what is the cause of water hammer.
Hydraulic shock occurs.
Been mentioned so far, the key idea of momentum, that you've got this body of water that's in motion in the pipe. It's headed towards the outlet, and the valve that was closed there, that ball valve, just with a quarter turn instantaneously will have the water going 10 feet per second, and then it's going 0 feet per second. And so all of the force of that water strikes up against that valve that's been closed, and then the shock wave goes the other direction. It may terminate at a water heater, at a reservoir, and then it reflects back again towards the valve a second time. So this is momentum. The water's moving and suddenly stops. And that's what causes this hammer. It's just like a physical hammer, force divided by area. You've got the force of the water stopping very suddenly.
By closing the valve slowly, the velocity of the water is reduced before the column is stopped. Water hammer may also be initiated by thermal shock.
All right, we're not going to talk about thermal shock, but that gives you the idea of some of the causes of water hammer. And let's talk about it on a fundamental level by looking at this diagram that comes from our textbook. Okay, so what I'd like you to envision is a tank that's open to the atmosphere, and there's a pipe coming from that tank. It could either be horizontal or it could be inclined. It doesn't necessarily matter. This is showing it as inclined just to make the point that the phenomenon exists regardless of the inclined path. And so there's some water velocity initially. We've got a valve that's open, and so flow is going through the pipe. And let's consider the pressure situation as flow is going through the pipe. We know that there's going to be head loss, and so here this is indicating that there's some H sub F. So the head loss that occurs is because of the pipe friction. As the water is flowing through the pipe, there's a resistance to flow at the boundary between the water and the stationary pipe material. And the pressure is decreasing in the direction of flow. So this valve is open. Then, if we consider a certain control volume, think about the flow that's going in and the flow that's going out of that control volume right now when the valve is open. The inflow and the outflow are equal at this current steady state. So if we were going to consider this through the momentum equation, there's not going to be any imbalance in forces right now because the outflow and the inflow are equal. And the momentum force only occurs when the inflow and the outflow velocity is different. So if the valve is suddenly closed, then what happens is, in this same control volume, for just a brief moment, there's an accumulation of force up against the valve because temporarily the flow in is greater than the flow out of that control volume. So there's an imbalance in the velocities, which causes an accumulation of force up against the valve. And that causes pressure to build up. And now what we have here is that when the valve is closed, there's no longer any frictional losses. And so looking here, this dashed line, the lowest dashed line, refers to the energy grade line. Now it's flat. And so it's flat because there's no bulk flow. The water isn't moving through the pipe anymore, even though if you go a little bit further away from the valve, the velocity is still forward. There isn't a net flow through the pipe. It's just this temporary, instantaneous moment where the momentum really hasn't caught up with the entire column. Remember, the water is just a little bit compressible. And so the pressure wave starts propagating backwards towards the reservoir, and the speed that it does that is called the celerity. And so here you can see C. That's referring to the velocity or the speed at which the shock wave is going back away from the valve towards the reservoir. Now there's an increase in the energy. This delta H is indicating that the pipe has swelled a little bit. This is a very interesting thing. Remember, we're talking about how water hammer is an increase in pressure inside of the pipe. Well, when the pressure goes up inside of the pipe because of this shock wave, what happens is the pipe expands. And so these little dashed lines here around the pipe, that's meant to draw your attention to the idea that depending on how flexible the pipe is, if it's a relatively soft pipe material like lead, it may expand a lot. If it's a relatively more rigid steel pipe, then it wouldn't expand as much. But the pipe is reacting to the shock wave as well by expanding. And so because it's expanded, there's actually more energy inside this part of the pipe than the pipe that's to the left of it. Because now it has this, you think of the pipe as an elastic band. And when you've stretched the elastic band, there's energy in that. It's going to snap back. And so the same thing is true here in this region where there was increased in pressure. The pipe expanded because the pressure went up. And so now it has a little bit extra energy on the right side of the pipe compared to the left side where the pipe hasn't yet expanded. So water is somewhat compressible, the pipe is somewhat elastic, and so the water compresses, the pipe expands, and that's what causes this increase in head in that zone that's closest to the valve. So as we go further steps through the process, there comes a point where the shock wave makes it all the way to the tank. You know, at this part, the shock wave was only part of the way through the pipe, but the shock wave is moving its way through the pipe, and this whole process is very, very fast. We're talking about milliseconds. So it's moving from the valve back towards the tank, and now at this point, the entire pipe is expanded because the shock wave is all the way through, and so everywhere inside of the pipe, there's an increase in head, and also there's a little bit more water inside of the pipe than there ought to be, because remember, the pipe expanded, it swelled, so to speak. And so what's going to happen is that pipe is going to start to not collapse, but it has swelled and expanded, and it's going to contract again, and that's going to force water into the reservoir. And so in the return journey, the shock wave goes from the reservoir back towards the valve again. And so here you can see the C is indicating the direction and the magnitude of that celerity as the shock wave moves from the reservoir back towards the valve, and then the water is flowing from the pipe into the reservoir as the pipe contracts. And so it's a wave of decreased pressure heading towards the valve this time. And that process is called wave reflection. And it can happen several times. In the video that we just watched a moment ago, when they closed that valve really quickly, you could see on the little plotter that they had that there was a big spike in the pressure, and then there was a little spike. It was kind of like aftershocks or several subsequent waves that progressively got smaller because some of the energy is dissipated. As you're doing the work of expanding the pipe, you lose a little bit of energy there, and so it's not that each shock wave is as big as the one before it. It's a gradually reducing process, but there can be several round-trip journeys as these shock waves pass between the valve, the reservoir, and back to the valve again. Okay, now in fluid mechanics, we talked about bulk modulus of elasticity and how it's a property of fluids that describes how compressible that fluid is. And so that if you know some increase in pressure, then you can understand the change in the specific volume of the fluid. And so if we think about water, for example, is a unit mass of water, so a kilogram of water occupies 1 liter of space, or 1,000 kilograms of water occupies 1 cubic meter of volume. So instead of saying mass per volume, specific volume is volume per mass. And so the bulk modulus of elasticity is that relationship of how an incremental increase in pressure changes the volume occupied by a unit mass of a fluid. And you can look up the bulk modulus of elasticity. Here is a table for the E sub V for water in the traditional units. You have a question related to this idea of water hammer in your homework, and so I wanted to point out that the table that's in your book, table 2.3, has bulk modulus for water, but there's actually an error in the textbook. They're saying that it's these numbers that are divided by 10 to the 9th, but actually it should be multiplied by 10 to the 9th to get the bulk modulus in terms of newtons per meter squared. So you can know the temperature of the water and what pressure it exists at and look up the bulk modulus. And we're going to do that with an example today. We'll do a sample calculation just to give you an idea of how quickly that water is able to move through the pipe. Okay, so celerity, it's the velocity of the pressure wave, and you can calculate the theoretical celerity as how quickly the shock wave would be traveling through a fluid of infinite extent, meaning that it exists in all directions. Because the shock wave travels through water that's in a pipe at a different speed than it travels through water that is open in all directions. And so the theoretical wave celerity depends on the bulk modulus of the fluid and the fluid's density. And it's going to have units of length per time. The units that you're going to get out of this would be like meters per second or feet per second, how quickly the water is moving. And it varies depending on the density of the fluid and the temperature of the fluid. But for water, a typical value is that a shock wave would move through unconfined water at about 1440 meters per second. So when you're given a problem, the first step is to calculate that theoretical wave celerity for the temperature and fluid conditions that are described. Then the next step is that you have to consider what kind of a pipe that you have. It's going to depend on the pipe modulus, and so here the E sub P is talking about the modulus of elasticity of the pipe, where E sub V was the bulk modulus for the fluid. Here is a table from our book, table 8.6, that's talking about the modulus of elasticity for different types of pipe. And so you can see, for example, that lead is a relatively flexible pipe, and it's going to expand and contract really easily because its modulus of elasticity is only 3.1 times 10 to the 8th. In comparison to steel and iron are much stronger, so that they're not going to expand and contract quite so much. So how the pipe is expanding and contracting has an effect on the effective celerity of the wave in a confined pipe. Also, you have to know the thickness of the pipe, because that's going to have an effect on how much the pipe expands and contracts as well, because a very thin-walled pipe is going to expand and contract more than a thick-walled pipe would be. And so notice that here in the denominator, this ratio that's on the right-hand side is the modulus of elasticity for water, the pipe diameter, and whatever units you have, like if your pipe diameter is inches and the thickness of the pipe is inches, that's okay. You don't have to necessarily convert it over to feet, or if it's centimeters, as long as the units in the numerator and the denominator are the same, then you can use a little shortcut there, and even have mixed units if you like. You could have your fluid modulus values in SI units and your pipe diameters in traditional units, as long as it canceled out, because it's going to be a ratio that you're looking for. So you calculate the celerity of the pressure wave, and then to know the travel time, we have to consider twice the physical length of the pipe, because it's the round-trip travel time that is the governing factor here. This valve is going to be closed, and so the question is, for the conditions that you've got, what is the amount of time that you should wait to close the valve? Because the shock wave needs to go from the valve and to the reservoir and back to the valve. And so if you close the valve in more time than this travel time, then you'll avoid the worst of the water hammer. But if you close the valve faster than this T sub L, then that's going to cause this maximum increase in pressure that's going to really be problematic. And you can calculate the magnitude of that pressure increase by multiplying the initial velocity of the fluid before the valve was closing with the celerity of the shock wave and the density of the fluid. And then that delta P is going to tell you how much the pressure could increase. And as I kind of hinted at before, the worst case scenario is that you close the valve very quickly. And by, what I mean by very quickly is faster than the round trip travel time. And if you close the valve slowly, meaning it takes you longer than the round trip travel time to close the valve, then you won't have this maximum increase in the pressure. So let's go through the process of calculating the magnitude of the pressure increase and also the travel time that's required to avoid that pressure increase for the system that's summarized here in this problem statement, where the physical length of the pipe is 2,000 feet. We know it's a 4-inch steel pipe, and here this thickness of the pipe is 0.2 inches, and we know the pipe modulus here and the water modulus and density. And the calculations that you're going to need to go through are kind of sorted, the formulas are in order here. You know, first things first, you need to calculate what is the initial velocity based on the 0.6 cubic feet per second, and if you know the cross-sectional area of the pipe, then you can calculate the velocity from that. So you'll calculate the theoretical wave celerity, the celerity for the confined pipe that's actually described in this problem statement, the maximum pressure increase, and we'll also determine the round-trip travel time. And I give you this hint, since we're working in the traditional units, keep in mind that here where we've got the density is 1.94 slugs per cubic foot, keep in mind that a slug that is accelerated at 1 foot per second squared has units of pounds force. So the fluid density here, we're going to need to keep that in mind as you do the calculation. So I'm going to pause for just a second, give you a chance to start working on the calculations here, and let's see if this water is flowing through the pipe at 0.6 cubic feet per second, how bad is it going to get? Like, what's the pressure increase if you just instantly close that valve? Alright, so you're coming back into the main room now, and let's take a look at the solution together and just see if things were headed in the right track. And of course, this plays into the homework assignment that you've got to submit next week. Okay, so we start just with a summary of our given parameters for this system, the pipe's length and the fluid properties and the pipe properties that we know. And so what I've calculated is the initial velocity is 6.875 feet per second. And then the theoretical wave celerity started by converting the fluid properties from pounds per square inch into pounds per square foot. So we have to multiply by 144 to make that conversion, because if there's a certain amount of pounds in a little square inch, there's going to be many more of them in a square foot, since a square foot is 12 by 12. And so we've multiplied by 144 there. And then you can just use the density in terms of slugs per cubic foot. In that case, you don't substitute in the unit weight, which is 62.4 pounds per cubic foot, but here we actually need to know the density of the fluid. And so this is the theoretical wave velocity if it's unconstrained in all directions, but then when you route that through a pipe, it slows down the shock wave slightly because of the expansion of the pipe. And so that effect is accounted for down in the denominator here, where we've included both the diameter of the pipe and its pipe thickness. And you see that I didn't necessarily bother to convert all of those into feet units, that leaving it in inches is fine because we've got a ratio of PSI to PSI and a ratio of inches to inches. So it can just stay as it is. And the output from that theoretical formula is that the velocity of the wave is 4397 feet per second. Okay, so the increase in pressure that we're going to get when it was initially going 6.875 feet per second, and we know the fluid density and the celerity of the shock wave, this is going to bring the pressure up really high. 407 psi is definitely in the danger zone. There's a good chance that whatever fittings we have could begin to leak or maybe even burst. If this pipe was welded together, those welds may not be rated for this pressure increase, and so we would need to really be cautious about closing the valve slowly to avoid that shock wave. And a lot of the computerized controls these days have the option of programming the rate of valve closure. And so the second part of this question that it's asking is what is the minimum amount of time that we would want to take to avoid that maximum increase in pressure. And so the closure time is the round trip travel distance divided by the celerity of the shock wave. And so as long as we close the valve, if it takes you more than 0.91 seconds, then this isn't going to be the pressure that's achieved. It'll be less than that. It's not that there's no pressure. So if you closed it in 1 second instead of 0.91 seconds, it's not like there's going to be zero increase in pressure. It's just that there would be a reduced pressure increase. And here's the formula that tells you, what would be the pressure increase if you close the valve more slowly. It's kind of an empirical equation, and we won't have any application of that in the homework assignment. Now, unfortunately, I've just burned through all of our time. It's 1:50, and I didn't get a chance to show you the example that has to do with the sizing of the surge tank. And so what I'm going to do is I'm going to include this example in the recording that I post for Friday's class. And so then you'll have all of the information you need for the homework that this all goes on. Remember that homework 5 has your Hardy Cross problems and then a quick look at water hammer and surge tank sizing, and that's due on Monday of next week. All right, so that's all we have for today. Friday's class is online, but I still will be answering questions via email. Feel free to get in touch if there's anything I can do to help. Hope everybody's doing well, and I will talk to you later.